In the grand realm of knowledge, there exists a figure, a beacon of wisdom, Dr. Charles Severance. Esteemed educational technologist and computer science virtuoso, he stands as a professor, wielding a PhD from the University of Michigan. His influence? Global. His impact? Profound, revolutionizing computer education for hundreds of thousands across the world. Now he unveils his latest masterstroke, Python for Everyone. A course designed to illuminate the path to Python proficiency for the novice and the experienced alike. Journey through the fundamentals of Python programming, delve into the depths of web development, data analysis, artificial intelligence, and beyond. Python, a titan of a tool, celebrated for its simplicity, readability, and a vast community of developers, making it particularly accessible for those with no prior knowledge. Unlock the power of Python. Your adventure into the world of programming awaits.
Oh, fiddlesticks. How do I print the exception message? I always am forgetting. Print failed to retrieve. Okay, so we'll put that in. Now if I run it, oh, and then I have to put a break here because that's not good. Break. Failed to retrieve. Now I got to figure out. Oh, I never know how to print out the error message. Yeah. So I have to. I never remember. See, that's the weird thing about stuff is that I don't ever remember enough. I don't remember the syntax, what I say here, to print the error message out. So I'm going to go to Google, and I'm going to say print out the exception message in Python. Print out the exception message in Python. Oh, Python 3, hello. Okay, so let's go find it here in the documentation. Accept. Is this it? Is this what I say? I just want to print out the message. Ah, that's it. Accept. Let's try this. So this is part of Python programming, is like, for me at least, because I'm just not like a genius expert at this stuff. Ha! This is one thing I like about Python, is you can guess stuff, and sometimes you guess right. So there we go. We got the error, we got the nice little error message, and we see error 429, too many requests. So that cleans that up nicely. So we have run out of requests, and on that, it is a good time to say thanks for listening, and I hope that you found this valuable. Hello, and welcome to our final chapter, Retrieving and Visualizing Data. In this chapter, we are going to basically bring this all together. Databases, web services, code, loops, logic, and we're going to solve a problem that is a multi-step data analysis. We're going to find some data on the internet, might be a...
Are you ready to unlock the power of programming? Welcome to Pro Free Courses Comp, the one-stop destination for all things coding. With us, you're not just learning, you're embarking on an exciting journey into the world of programming. Imagine having access to over 100 comprehensive courses from the world's top universities all at your fingertips. From Microsoft Office to Google Workspace, from Python to JavaScript, from React to Node.js, from beginner to advanced, it's all here and it's all free. This isn't just about learning to code, it's about mastering the language of the future. Joining pro-free courses. Comp means becoming part of a community of learners, developers, and innovators. It means stepping into a world where learning never stops, where every line of code you write opens up a new universe of possibilities. So why wait? Subscribe now and take the first step towards coding your future. With Pro-Free Courses Comp, you're not just learning to code, you're learning to create, innovate, and transform the world. Pro-Free Courses Comp. Learn, code, your path to success.
HTML might be an API or whatever, and we're going to write a relatively slow process that's going to pull data slowly, because these are all rate limited. This is a slow and restartable process. So you can start this, and what we're going to do is we're going to have a database that's going to hold the data that we're pulling, and so this might take several days actually, if you really have to do it, and then you'll build up your data in your database, and then what you tend to do is you tend to produce two databases. One is kind of a raw database that, it's all of its data columns are aimed at helping you figure out what you've got to retrieve yet and what you haven't retrieved yet. So that's kind of a crawling, spidering process. And then you find that the data is kind of nasty and ugly, and you find that before you're going to do any analysis, you probably want to clean and process it. So in a lot of these, you're going to go from a raw database to a clean one. And this is going to be really large, and this is going to be really small. And you're going to do this sort of once, but slowly, and you'll do this as many times as you need, changing this program, cleaning the data up over and over and over again. And then you'll end up with really clean data, and it's relatively small. And you might run programs that'll loop through this to do visualizations or analysis or some things or whatever. And so you'll actually sort of use this database as a source of information. Okay? So that's the basic pattern of what we're going to work with. Now, this is what I call personal data mining. And if you're going to do this seriously, Python is used in lots of data mining activities, but if you're going to do data mining seriously with really, really large data sets, we're doing small to medium-sized data sets, as you might do sort of for individual personal research versus like an organizational research where you're processing the logs of a web server or something like that. And there's lots and lots of wonderful technology. And what's really cool is this technology just keeps getting better and better, because the whole data mining, data analysis, natural language processing field is just so hot right now. It's so awesome. We're going to keep it simple and do stuff for ourselves for now. And I gave you a bunch of sample code that's going to make it so that you can adapt this sample code to solve the problems that you need to solve. So like I said, this is more of a programming exercise. Data mining might be a lot more complex. If you're doing simple research, this might actually model what you do pretty well. So the first thing that we're going to do is what's called use the Google's JSON API for geocoding. And there are two versions of this. One version requires a key, and one version doesn't require a key. Google used to make all this data available for free, but with just a rate limit, but now they're increasingly requiring a key. So I give you code in this zip file that kind of does both. If you really wanted to do something in production of taking user entered places and names and getting precise latitude, longitude coordinates, so you can produce a nice little Google map like this. Since Google has made a rate limited API, I've actually pre-spidered a copy of the Google data, and I have my own sort of fake Google API, and so you can do your assignments and test all your code using my fake API, which has no rate limits and has no problems, but it's only a limited set of the data. And so this is the basic process, and it's one of those things that it follows that basic personal data modeling, personal data mining pattern. And so here's this API, which is either Google or me. I've got my own Dr. Chuck version of this, drchuck.net version of this, and there is an input queue of the location. So this is the user data where they just put in the name of where they think they live, University of Tübingen or something. And so this is the queue of the things that are to be retrieved. And in my case, when I built this map for the first time, there was like 15,000. And it took me days to get this. And so it would stop. And so what I would do is I would, read the first one into this geoload.py, check to see if I already had it in my database. If I didn't already have a database, I would go into the API, I'd pull the data down, and I would put it in the database. And then I'll go to the next
Smash
one.
that like button,
The next one, the next
drop a
one.
comment down
I
below,
might get
and subscribe
1,000
to
in my
Pro Free
database,
Courses
and then it
Comp
blows
now.
up, or I'm told I can't go any further. So I wait 24 hours, I start it up, and it reads the first 1,000 and says, oh, they're all in the database already. And then it starts at 1,001. And then it adds that, and adds that, and then until it stops. And so it took me several days of processing to get this data right. Now, I didn't have a separate cleaning process because this data is pretty simple. I was pulling out the JSON, the latitude and longitude, etc. And so I didn't have to do two separate processes to clean this data up. It was clean enough right as I pulled it. Because I was talking to an API. If you're talking to the HTML, sometimes it gets nasty and ugly. And so then I wrote this program that just reads through it. It just does a select and reads through the stuff, and it prints out some summary information and tells you what to do. It also prints out, and you'll see this pattern, because I'm visualizing using browsers, HTML, and this happens to be using the Google Maps API. And putting all the data in a little JavaScript file. So these end up being assignment statements in JavaScript. You can take a look at that file. And all the data shows up as assignment statements in the JavaScript. And then when this HTML loads, it reads this file and puts up all those pins, as long as you have access to the in-browser JavaScript API. So the next thing we're going to talk about is PageRank, which is spidering now HTML. We talked a lot about this. Spider HTML, get some links. And so up next, we're going to actually build a real database, full-featured search engine using PageRank. This is another worked code example. You can download the sample code zip file if you want to follow along. And the code that we're working on today is what I call the...
Are you ready to unlock the power of programming? Welcome to Pro Free Courses Comp, the one-stop destination for all things coding. With us, you're not just learning, you're embarking on an exciting journey into the world of programming. Imagine having access to over 100 comprehensive courses from the world's top universities all at your fingertips. From Microsoft Office to Google Workspace, from Python to JavaScript, from React to Node.js, from beginner to advanced, it's all here and it's all free. This isn't just about learning to code, it's about mastering the language of the future. Joining Pro Free Courses Comp means becoming part of a community of learners, developers, and innovators. It means stepping into a world where learning never stops, where every line of code you write opens up a new universe of possibilities. So why wait? Subscribe now and take the first step towards coding your future. With Pro Free Courses Comp, you're not just learning to code, you're learning to create, innovate, and transform the world. Pro Free Courses Comp, learn, code, your path to success.
Geodata code, and that is code that is going to pull some locations from this file. We're simulating or using the Google Places API to look places up, and so we can visualize them on a map. And so this is the basic picture. If we take a look at this where.data file, it's just a flat file that has a list of organizations, and this actually was pulled from one of my MOOC surveys. We just let people type in where they went to school, and this is just a sample of them. So this data is read in by this program geoload.py. And if you recall, this Google Geodata has rate limits. It also has API keys, which we'll talk about in a bit too. And so the idea is this is a restartable spider-like process. And so we want to be able to run this and have it blow up and run it and start it and not lose what we've got, right? And so this is unlike some, so we're not now using a database as well as an API, but in order to work around the rate limits of this API, we're going to use the database with a restartable process. And then we'll make some sense of this, and then we'll visualize this. But in the short term, let's start with geoload.py code. Geoload.py, take a look here. So a lot of this hopefully by now is somewhat familiar to you. URL lib, JSON, SQLite. And so I mentioned that the Google APIs, these used to be free, and did not require an API key, but increasingly they're making you do API keys for especially new ones. And so what happens, you can go to your Google Places, go to Google APIs and get an API key, and you can put it in here. It'll be this big long thing that looks like that. And then if you have an API key, you can use the Places API. And I've got a copy of a subset, not all of it, a subset of it here at this URL. As a matter of fact, you can just go to this URL in a browser, and it will tell you a list of the data that it knows about. Okay, and I made it so that does the same basic protocol with the address, address equals as the Google Places API. So this will just change how we retrieve the data. Either retrieve it from my server. Nice thing about my server, it's got no rate limit. It's really fast, and you're not fighting with Google all the time, and it means that perhaps if you're in a country that Google is not well supported, you can use my API. I mean, that's really strange that somehow my API is more reliable and available than the Google one, but it's true. So we're going to make a database. We're going to do a create table if not exists, and we'll have some address, and we're really just caching the geographical data. We're going to cache the JSON. One of the things we do when we build these processes is we tend to simplify these things and not do all the calculation and parsing of the JSON. Just load it and get it in, and load it and get it in, and fill the data up in this database. And so that's what we're going to do. Because Python doesn't ship with any legitimate certificates, we have to sort of ignore certificate errors. We're going to open the file, and we're going to loop through it and pull out the address from the file, and we are going to select from the geodata where that address is the address. Let's move this in a bit, and so we're going to do a select and pull out that address, and the idea is if it's already in the database, we don't want to do it, so we do a fetch one and pull out that first thing, which is that will be the JSON right there. If we get that, we'll continue up, otherwise we'll keep going. Pass just means don't blow up, so we accept and we just do a pass. That's like a no-op. And we're going to make a dictionary, because that's what we do for the key value pairs. Everything you've seen so far, I've used constants here, but because we may or may not have an API key, query equals, and then that's the address, and then the key equals, and then the API key. If you recall, URL encode adds the pluses and question marks and all that nice stuff. We're going to retrieve it. We're going to read it and decode it, print out how much data we've got, and add a count. And then we're going to try to parse that JSON data and print it if something goes wrong. And as we've seen, at this top level of this JSON data from this geocoding API is an object, which we'll see a little bit of it in a bit. And it has a status field in it. And the status is okay if things went well. So if the status is not there, that means our JavaScript is not well formed or not how we expect it. If the status is not okay or not equal to 0 results, then print out failure to retrieve and then quit. And then we're simply going to insert this new data that we just put in, and then we're going to commit it. And every 10th one, this is count mod 10, we're going to pause for 5 seconds, and we can hit Control-C here, and then we're going to do the geodump. Okay, so let's just run this. Geodata Python. So let's do an ls. So we don't have, oh, we do have, let's get rid of from a previous test, geodata.sqlite. So we'll start with a fresh set of data and run python geoload.py. Of course, I'm always forever making the mistake of forgetting Python 3. So you can see that it's running, and it's adding the query, and in this case I don't have the API key, and it's putting the pluses in, and that's this part here with all the pluses. That's the URL encode, and you notice it's pausing a bit. Now, it depends on how fast your net connection. This may or may not go so fast, but this is not that much data, so it's like only 2,000, 3,000 characters. And so it's working and talking to my server. And the interesting thing here is I can blow this up. I'm going to hit Control-C, In Windows, you'd hit Control. In Linux, you'd hit Control C, and in Windows, I think you'd hit Control Z, depending on what shell you're working in. But I'm going to hit Control C, and you see I sort of blew it up, right? And that's causes a traceback, a keyboard interrupt traceback. If I do an ls-l, you can see that now this geodata is there. Now, in the name of restarting, I will restart this, and you will see that it checks and skips, and so it runs this code here, where it's right here. It grabs it and finds it in the database. So you'll see it say found in the database really quick, chop, 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 and go really fast, and then it'll go back to catching up where it left off. And so all those up there, they did not actually retrieve it because it knew about those things. And so now it's catching up and doing some more and doing some more and doing some more. And then I'll hit Control C. It has a little counter in here that basically, if it hits 200, it stops and you have to restart it. You could obviously change this code. You could make it so it didn't sleep. Doesn't hurt to sleep for like a second after every 100 or so if you want. You could change that code. And now let's just hit Control C and blow it up, ls-l. And there is another bit of code, and this code, it's always good to write these really simple things. And so now we're going to import SQLite and JSON. We're going to connect ourselves up. We're going to open, except this is a UTF-8 because it's a UTF. We're going to open this with UTF-8, and we're going to read through. And in this case, we are going to decode. We did select star from locations, and if you recall, locations has a location and a geodata. And so the sub 0 will be the location and the sub 1 will be the geodata. And we're going to parse it, convert it to a string, and then parse it. If something goes wrong with the JSON, we'll just keep skipping it. We'll check to see if we have the status in our JSON. Let me run the SQLite browser here. File open database. Let's take a look at what's in this database. Oh, where are we? Code 3, geodata SQLite. So this is the data we've got. So if you make this a little bigger, if I can I make that bigger? Yeah, it's not going to show us much. So you can see that these are the addresses in the geodata. That's just the JSON. So that's the JSON that we got, and it retrieves it. And so this is a really simple database. That's just a sort of spidering process, run. But now we're going to run the geodump code, which is going to read this and dump this stuff out and print where.js, so it's going to actually parse this stuff. And that's code we've seen before. And so we're actually reading it, and this line goes into the results. Results is an array, so if we go into results is an array. We're going to go grab the 0th item in that array, and then we're going to go find geometry, and then location, and then lat and long for the latitude and longitude. And then we're also going to take the actual address out of the formatted address right here. So in this bit of code, we're actually parsing the JSON, and we're going to clean things up, get rid of some single quotes. This kind of data cleaning is just stuff after you play with it for a while, you realize, oh, my data is ugly or does this. I'm going to print it out, and then I'm going to write this out, and I'm going to write it into a JavaScript file. And so the JavaScript file is this where.js, and this, I'll show you what it looks like. It's going to be overwritten. This is the one that came out of the zip file. It'll have the latitude, the longitude, and we're going to use JavaScript to read this in this where.html file. It's going to actually read this right there and pull that data in, and that's how we're going to visualize. I'm not going to go into great detail on how the visualization happens, but that's what's happening, and so we're going to write that. So we're going to actually write this to a file. So let's go ahead and run this code and say Python 3 geodump. Okay, so it wrote 120 records to where.js. So if we look at where.js, this is now the new data that I just downloaded moments ago. And it says open where.html in a browser. Now you'll need the Google Maps API, and you might not be able to see this depending on where you're at, but here you go with Google Maps locations, and I think if you hover over this, you can see, and you see the UTF, why we there in that particular thing, why we had to use the UTF-8 when we wrote the file, so that we didn't end up with trouble writing the file out. And so there you go. And so that is a simple visualization, and just a simple visualization. It wrote this where.js. If you are smart with HTML and JavaScript, you can look at this where.html file. It's really just reading through a bunch of data and putting the points. That's all there is, but I'm not going to go through that. So, at least not in this. And so I hope that this was useful to you, and thanks for watching. So now we're going to write a search engine. Do some of the things. We're going to do PageRank, and we're going to visualize it in a web browser and show the weights. We're really only going to do PageRank on one page because you want to have links that more than one page that points to a page, so that you can figure out which pages are more or less important. And then we'll visualize it. We'll run the PageRank algorithm, and we'll separately do all this. So at this point, we're going to do pretty much the web crawling, the index building, and the searching. We're not going to really search it. We're going to visualize the index. But you could write a simple program to do searches for keywords and figure out which page was the most likely page for a keyword. And that would be a fun additional thing to do. So the web crawler is this program that hits a page, pulls down the HTML, parses the page, looks for links, makes a queue of incoming links that are as yet unretrieved, and I'm going to do this in a simple SQLite database, and starts out with, the database basically starts with one link as the starting point, and then it retrieves that page, and then you see the database end up with lots of unretrieved pages, and then it goes back in and picks a random page and retrieves that one, and then it just expands and expands. This code that I've built that you're going to play with only stays on one website, otherwise it would go crazy. But of course Google doesn't use an SQLite database running on your hard drive. But you'll get the idea. You'll see this thing exponentially gain links, and you'll run it for a while, pull down 1,000 web pages or whatever. But of course, make sure that you don't violate any terms and conditions. And again, I've got some data sources that you can use, and they're not rate limited, but you can also use things like Wikipedia, which I think they sort of discourage you, or drchuck.com, which has no rate limit, or who knows what, right? So just be careful. Don't do this on Facebook, and don't do it on Google. Don't get yourself in trouble. And if you're using, you know, a internet connection where you're paying for bandwidth, be careful. So this is the idea of the web crawler, and this isn't my picture. This is the classic picture of a web crawler. Read a page, parse it, take all the URLs and stick them in a queue, grab again and again. So for us, the scheduler is going to do it as long as you'd say, oh, do 100 pages, or it runs until it blows up. I mean, and again, these processes that have the network in the loop, it's really important that they behave well when they blow up. And that's why databases are so useful, because you can be writing along to the database and some random thing happens and blows your data up, and you start over. So you're reading these things, you're storing each page, building up your storage, etc., etc. So you just keep on doing that. And with this program, you'll be able to retrieve some stuff, then run the PageRank, then you can retrieve some more, and then you can run some more PageRank, and you can kind of see how Google sort of evolves its index over time. Of course, we're so much simpler. And like I said, be careful when you crawl. You're going to run a crawler that just goes as fast as it can. But Google doesn't do that. It's careful not to overwhelm any websites. It's trying to be smart about the use of your bandwidth on your website. There is a file. Our code won't bother looking at this. But there's a file called robots.txt that real web crawlers look at, and it gives a list of the things you are allowed to look at and not allowed to look at. And so if you go to Google and you see a search that says, we are not allowed to show you the summary text of this page because of the robots.txt, it's there, and you can go and you can actually see a robots.txt. Like on, just go to any website, it's at the top root, blah, 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 /robots.txt. It's not a path, it's not slash this, slash that, slash something else robots. It's at the very, very top of a website. The index building uses the PageRank algorithm, and the whole goal of the PageRank algorithm is to figure out which pages have the most best links. So having the most links is really easy. You can just say how many links go to this. But the problem is you got to figure out the value of those links, and then you have to
Smash
figure
that
the value
like
of those
button,
links
drop a comment
by
down
looking
below,
at how
and subscribe
many
to
good
Pro Free
links
Courses
come to
Comp
bid.
now.
So it turns out that it's an infinite problem. It's an infinitely difficult problem to use PageRank, but you can approximate it, and what happens is after a while it converges to a reasonable value. And so we're going to run the search index, and each time it runs you're going to see that it says, you know, how much did these numbers change? And what happens is in the beginning they change very wildly, but quickly they flatten out. And it has the best way to think about the PageRank is think about how water runs, where you have a small little stream going by a house, and sometimes it rains, sometimes it's dry, and sometimes, you know, and there's like a little lake, and the stream is always running, and it doesn't go up and it doesn't go down. It might go up a little bit if it rains a lot, but in general there's sort of a steady state, meaning that whatever water's coming in is about the same as the water going out. So we think about this in terms of web pages. The value of the links coming in is roughly the same as the value of links going out. So when that starts to balance the in and the out value from each of the nodes, then you've got pretty stable. And so what Google does is they have a really relatively stable assessment of goodness and value of pages, and they use that to compute PageRank, and then they throw a few more pages in, and it kind of has to adjust for a while, but it reconverges. And so this is a calculation that generally converges, and it doesn't vary wildly. And that's why Google's pretty good at kind of arriving at the true value of something. So let's take a look at what we're going to do in this application. Again, we have a file that is going to spider the web, and we only have one database. Again, in this one, we'll have two databases in the next one. And so this is spider is the restartable part. And what we actually do is we put one URL in, the starting URL, and then spider walks in and asks, are there any unretrieved pages? And it does that randomly. It sort of picks among the unretrieved pages and says, okay, great, I'll go retrieve that page. And then I'll parse that page, and then I'll put in a bunch of new unretrieved pages, okay, as well as the text of that page, and then a bunch of unretrieved pages. And then it'll go back up and it'll say, oh, give me one of the randomly non-retrieved pages, and it'll grab a next page and pull that page down and then add to it. And so this is like there's a page and then a to-do list. And then this one becomes a page and then adds a few more things to the to-do list. And so the to-do list, or the unretrieved URLs, grows very rapidly. And the retrieved ones grow sort of as you retrieve them one at a time. But you've always got this long list. If you have a really short site that only has like 2 links, if you start at drchuck.com/page1.htm, it'll go to page 2 and then go back to page 1 and it'll be out of things. It'll have retrieved all of the pages. And so if you have a website that has no external links or has very few pages and they point to each other, this will run out of things to do. But if you go to a page like my blog or the code that the sample stuff that I have up for you to spider for testing on drchuck.net, it'll run for a very long time, and you'll have far more pages to retrieve than pages that you retrieve. But that's okay. At some point, you can stop this. Maybe it stops because you ran out of bandwidth, or maybe your computer went down, or who knows what, right? But it's okay. This is a restartable process because it always has some pages that are retrieved and some unretrieved pages. You start it back up, it picks randomly from the unretrieved pages. Your database is the sort of persistent state of your spider rather than a bunch of dictionaries or lists inside the Python, which go away when the program dies. And so at some point you have, let's just say, a few hundred pages in here and a few thousand unretrieved pages. You can run the PageRank algorithm. And what the PageRank algorithm does is it loops through all the pages and figure out which pages are linked to which pages, and then reads the numbers and then updates the numbers, and then does that some number of times. And so this is where the numbers, all the pages sort of start out with goodness of 1. I think this printout is showing that goodness of 1, and then it changes, and then the goodness goes to some of the goodness goes up to 2, some of the goes to 7, and whatever. But then it does this over and over, and then it uses these numbers, and then they change again. And so there's a number of time steps that this PageRank runs. And you will see, as the page rank runs, when I show you the code, you'll see the average sort of change in these numbers across all these things, and you'll see that the average goes down very rapidly as you get through. And so usually with a few hundred or even thousand pages, like 100 plus times running this algorithm, and these numbers have converged. And that's when you sort of can begin to trust the numbers. Now there's this one program called SP Reset, which sets all the pages back to 1, so you can start this over. So if you were to spider for a while, run SP rank for a while, play around, and then you wanted to spider some more and start it over, you could say, oh, let's start the page rank completely over. Or you could simply take the new pages and watch it adapt. Either way, this is just a way to reset all the pages to have sort of their initial value of a goodness of 1.0. So at some point you run this. This runs really, this part here runs really slow. This part runs super fast, like in the blink of an eye. This one is pretty fast. And then at some point you've got these pages that have, you know, numbers on them. They have values on the pages. And there's a couple of programs that allow us to visualize that. One is the dump, which just reads it and checks to see. It shows the new page rank, the old page rank, and various other things, and shows just a way to dump it. And then there's this thing that reads the whole thing. You say, I'd like to do 25 of the top, the best. It sorts it by page rank, and then produces a JavaScript file that has just the numbers in it. And then there is some HTML and a visualization library called d3.js, which you can read about, that when the HTML starts, it reads this and has this nice force-directed layout of the page rank. And you can hover over things and you can see what page rank you've got. And so that is the PageRank algorithm that we're going to do. And up next we'll do the largest and most complex of these things, and that is the email. We're going to spider some email, which is about 1 gigabyte of data. Okay? We're doing a bit of code walkthrough, and if you want to, you can get to the sample code and download it all so that you can walk through the code yourself. What we're walking through today is the PageRank code. And so the PageRank code, let me get the picture of the PageRank code up here. Here's the picture of the PageRank code. And so the PageRank code has 4 chunks of code that are going to, 5 chunks of code that are going to run. The first one we're going to look at is the spidering code, and then we'll do a separate look at these other guys later. So the first one we'll look at is spidering. And again, it's sort of the same pattern of we've got some stuff on the web, in this case web pages. We're going to have a database that sort of just captures the stuff. It's not really trying to be particularly intelligent, but it is going to parse these with Beautiful Soup and add things to the database, okay? And so then we'll talk about how we run the PageRank algorithm and then how we visualize the PageRank algorithm in a bit. Now, the first thing to notice is that I've got to put, I put the Beautiful Soup code in right here, okay? So this is, you can get this from the bs4.zip file. There might be a README, no, but there's a README somewhere. But you got to use Beautiful Soup, you got to put this bs4 zip, or you have to install Beautiful Soup for your stuff. So I provide this bs4.zip as a quick and dirty way if you can't install something for all of the Python users on your system. So that's what it's supposed to look like. You're supposed to have it unzipped right here in these files, and I don't know what dammit.py means. That came from Beautiful Soup. If you look, it's in their source code. So I'm not swearing. It's Beautiful Soup people are swearing. I'm sorry. I apologize. Okay, so the code we're going to play with the most is, in this first one, is called spider.py. And, you know, we're going to do databases, we're going to read URLs, and we're going to parse them with Beautiful Soup. Okay? And so what we're going to do is we're going to make a file. Again, this will make spider.sqlite, and if here we are in PageRank, and else minus L. Spider.sqlite is not there, so it's going to create the database. We do create table if not exists. We're going to have an integer primary key because we're going to do foreign keys here. We're going to have a URL, and the URL which is unique, the HTML which is unique, whether we got an error. And then for the second half, when we start doing PageRank, we're going to have old rank and new rank, because the way PageRank works is it takes the old rank, computes the new rank, and then replaces the new rank with the old rank, and then does it over and over again. And then we're going to have a a many-to-many table, which points really back. So I call this from ID and to ID. We did this with some of the Twitter stuff. And then this webs is just in case I have more than one web, but that really doesn't make much difference. Okay, so what we're going to do is we're going to select ID URL from pages where HTML is null. This is our indicator that a page has not yet been retrieved. And error is null, ordered by random. And so this is our way, this long bit of stuff. And this, not all this SQL is completely standard, but this order by random is really quite nice in SQLite. Limit once is just randomly pick a record in this database where this true is true, and then pick it randomly. And then we're going to fetch a row. And if that row is none, right, we're going to ask for a new web, a starting URL, and this is going to fire things up, and we're going to insert this new URL. Otherwise, we're going to restart. We have a row to start with, and otherwise we're going to sort of prime this by inserting the URL we start with, and insert into it. If you enter it, just goes to drchuck.com, which is a fine place to start. And then what we do is what this does is its page rank is it uses this webs table to limit the links. It only does links to the sites that you tell it to do links. And probably the best for your page rank is to stick with one site. Otherwise, you will just never find the same site again if you let this wander the web aimlessly. And so I generally run with one web, this should be probably called websites. And I pull in all the data and I read this in and I just make myself a list of the URL, the legit URLs, and you'll see how we use that. And the webs is what are the legit places we're going to go? Because we're going to go through a loop, ask for how many pages, and we're going to look for a null page. Again, we're using that random, order by random, limit 1. And then we're going to have we're going to grab one. We're going to get the from ID, which is the page we're linking from, and then the URL. Otherwise, there's no one retrieved. And so the from ID is when we start adding links to our page links, we got to know the page we started with. And that's the primary key. We'll see how that primary key is set in a second. So otherwise, we have none. And we're going to print this from ID, the from ID and the URL that we're working with. Just to make sure, we're going to wipe out all of the links. Because it's unretrieved, we're going to wipe out from the links. The links is the connection table that connects from pages back to pages, and so we're going to wipe out. So we're going to go grab this URL. We're going to read it. We're not decoding it because we're using Beautiful Soup, which compensates for the UTF-8, and so we can ask. This is the HTML error code. And we checked that 200 is a good error. And if we get a bad error, we're going to say this, error on page. We're going to set that error. We're going to update pages. That way we don't retrieve it ever again. We basically check to see if the content type is text HTML. Remember, in HTTP, you get the content type. We only want to look for the links on HTML pages. And so we wipe that guy out. If we get a JPEG or something like that, we're not going to retrieve JPEG. And then we commit and continue. And so these are kind of like, oh, those were pages we didn't want to mess with. And then we print out how many characters we got and parse it. And we do this whole thing in a try except block because a lot of things can go wrong here. It's a bit of a long try except block. Keyboard interrupt, that's what happens if I hit Control-C at my keyboard or Control-Z on Windows. Some other exception probably means Beautiful Soup blew up or something else blew up, and so we indicate with the error equals -1 for that URL so we don't retrieve it again. At this point, at line 103, we have got the HTML for that URL, and so we're going to insert it in, and we're going to set the page rank to 1. So the way page rank works is it gives all the pages some normal value, and then it alters that. We'll see that in a bit. So it sets it in with 1. We're going to insert or ignore. That's just in case this pages is already the pages is not there, but and then we're going to do an update, and that's kind of doing the same thing twice, just sort of doubly making sure if it's already there, this or ignore will cause this to do nothing, and the update will cause us to retain it, and then we commit it so that if we do selects later, we get that information. Now this code is similar. Remember, we use Beautiful Soup to pull out all the anchor tags. We have a for loop. We pull out the href, and you'll see this code's a little more complex than some of the earlier stuff because it has to deal with the real nastiness or imperfection of the web. And so we're going to use URL parse, which is actually part of the URL lib code, and that's going to break the URL into pieces. Come back. We use URL parse. We have the scheme, which is HTTP or HTTPS. If it's this solves relative references. This solves relative references by taking the current URL and hooking it up. URL join knows about slashes and all those other things. We check to see if there's an anchor, the pound sign at the end of a URL, and we throw everything past, including the anchor, away. If we have a JPEG or a PNG or a GIF, we're going to skip it. We don't want to bother with that. We're looking through links now. We're looking at all the links. And if we have a slash at the end, we're going to chop off the slash by saying -1. And so this is just kind of nasty choppage and throwing away the URLs. But we're going through a page and we have a bunch that we don't like, or we have to clean them up or whatever. And now, and we've made them absolute by doing this. It's an absolute URL. This is just, you write this slowly but surely when your code blows up and you start it over and start it over and start it over. Then what we do is we check to see through all the webs. Remember, those were the URLs that we're willing to stay with, and usually it's just one. If this would link off the sites of the sites we're interested in, we're going to skip it. We are not interested in links that leave the site. So this is like link that left the site, skip it. But now we finally, here at page line 132, we are ready to put this into pages, the URL and the HTML, and it's all good, right? And that one's going to be null right there because we haven't retrieved the HTML. This is null because this is a page we're going to retrieve. We're giving it a page rank of 1. And we're giving it no HTML, and that way it'll be retrieved, and then we commit that, okay? And then we want to get the ID, so we could have done this with one way or another, but we're going to do a select to say, hey, what was the ID that either was already there or was just created, and we grab that with a fetch 1 and say retrieve to ID, and now we're going to put a link in, insert or ignore into links, from ID to ID, which is the ID, the primary key of the page that we're going through and looking for links. To ID is the link that we just created, and away we run. So it's going to go and go and go and go. Let's go look at the create statement up here, from ID and to ID right there. Okay, so let's run it. Python 3 spider Python. So it's fresh, and so it wants a URL with which to start, and I'll just start with my favorite website, www.drchuck.com. Now this first one you put in, it's going to stay on this website for a while, okay? So I'll hit enter, and let's just grab let's grab one page, just for yucks. Okay, so it grabbed that, and it printed out that it got 45 characters, and it printed out that it got 6 links. So if I go to this and open database, and I go to code 3, and I go to page rank, and I look at this, let me get out so it closes. So notice this SQLite journal. That means it's not done closing, so I'm going to get out of this by pressing enter, and so you'll notice now that that journal file went away. Otherwise, We would not be getting the final data. There we go. Okay, so webs, let's take a look at the data. Webs has just one URL. That's the URLs that we're allowing ourselves to look at. You can put more than one in here if you want, but most people will just leave this at one. Pages, so we got this first one and we retrieved this, and this is the HTML of it, and we found 6 other URLs in there that are drchuck.com URLs, right? There was lots of other URLs in there, but there were only 5 other ones that that we found, okay? And so, and what we'll find is if we go to links, we'll see that page 1 links to 2, links to 3, links to 4, links to 5, links to 6, because the links is just a many-to-many table. So page 1 points to page 2, page 1 points to page 2, page 1 to 3, page 1 to 5, okay? So that's what happens when we have the first page. So let's retrieve one more page. Now, we could have started a new crawl, but it's gonna stay on drchuck.com, and I'll just ask for one more page. And so now it went and grabbed. It randomly picked among these null guys, and I'm gonna hit enter to close it, and then I'll refresh this. And oh, so it looks like we retrieved OBI sample, and we didn't get any new links. And so the links page, no, we didn't get any new links. So that page, whatever that was, OBI sample, had no external links. So let's do another one. Oh, one more page. So that one had 15 links. So let's take a look now. So now we have 15 pages. It picked this one to do, right? And now it added 15 more pages. And then if you look at links, you will see that page 4, which is one it just retrieved, links back to page 1. So now we're seeing this is where the page rank is going to be cool. 4 links to 1, 4 links to is whatever, away we go, right? 1 goes to 4, 4 goes to 1. I should have probably put a uniqueness constraint on that. It's not supposed to that duplicated that. Okay. So let's run this a bunch of times now. So let's just run it 100 times for 100 pages. It'll take a minute. So you'll see it's like freaking out on certain pages and not parsing them. You know, it's found its way into my blog. It's finding like 27 links. This table is growing wildly at this point. It's going to take us a while before we get to 100. It's kind of slow. Now the interesting thing is I can hit Control-C at any point in time. Right? And so that blew up. But it's okay because the data is still there. And so if we go back to pages, for example, and we refresh our data, we see we got a ton of stuff. And this will restart and all the things. So if we search this, that I sorted that by HTML, you see that there's lots of files that we've got, and it's never going to retrieve those again because those have HTML. So then I can run this thing again and start it up. And when I say Control-C, your computer might go down, your network might go down. There's all kinds of things that might happen, and you just pick up where it leaves off. It just picks up where it leaves off, and that's what's nice about this. Okay, so that's pretty much how this works. We've got this part running. We're seeing it flow into Spider.SQLite. We're seeing that we can start this and replace this. And so what I'll do is I will come back in the next video and show you how all these things work together and then how we actually do the page rank. So thanks again for listening, and see you in the next video. We're picking up in the middle here where we are running a simple spider that's retrieving data and putting it into running this spider.py file, and it's cruising around and doing things. And the beauty of any of these spider processes is I can stop anytime and just hit Control-C.
Are you ready to unlock the power of programming? Welcome to Pro Free Courses Comp, the one-stop destination for all things coding. With us, you're not just learning, you're embarking on an exciting journey into the world of programming. Imagine having access to over 100 comprehensive courses from the world's top universities all at your fingertips. From Microsoft Office to Google Workspace, from Python to JavaScript, from React to Node.js, from beginner to advanced, it's all here and it's all free. This isn't just about learning to code, it's about mastering the language of the future. Joining pro free courses. Comp means becoming part of a community of learners, developers, and innovators. It means stepping into a world where learning never stops, where every line of code you write opens up a new universe of possibilities. So why wait? Subscribe now and take the first step towards coding your future. With Pro Free Courses Comp, you're not just learning to code, you're learning to create, innovate, and transform the world. Pro Free Courses Comp. Learn, code, your path to success.
And so we take a look at the spider.sqlite file and retrieve it, and it looks like we got 302 pages. I don't know how many we got retrieved. 70. Okay, there we go. We got about 100. Oh wait, I'm looking for the wrong thing. No. Yeah, we got about 107 pages. So what we're going to do now with 107 pages is we are going to run the PageRank algorithm. Okay, so let's take a look at that code. So the idea of PageRank, we're going to run this PageRank algorithm. The SP reset just resets the PageRank, and SP rank runs as many iterations of PageRank. So the basic idea is that if you were to look at the links here, you know, we think of page 1 pointing to page 2 gives some of page 1's love to page 2. Page 4 has some value that it gives to page 1. You go on, and page 2 gives love to page 46, over and over and over again. And so, but the problem is that how good is page 1, and how much positive karma does it give to page 2? And so what happens is we start by giving every page a rank of 1. We say, look, everybody starts out equal. But then what we do is we divide up in one iteration of the PageRank algorithm, we divide up the goodness of a page across its outbound links, and then accumulate that, and that becomes the next rank. Okay, and so let's take a look at the code for the PageRank algorithm. So this is pretty simple. It only imports SQLite 3 because it's really doing everything in the database, right? It's going to be updating these columns right here in the database. And so so we're going to do some things here to speed this up. This rank runs, if you're thinking of Google, this rank runs slowly and is going to run continuously to keep updating these things. So the first thing I do is I read in all of the from IDs from the links, select distinct, throws out any duplicates, and so I have all the from IDs, which are all the pages that have links to other pages, because all the pages are in pages, but in links to have a from ID, you have to also have a to ID. Okay, and so we're also going to look at the pages that receive PageRank, and we're kind of pre-caching this stuff. Okay, and so we're going to do a select distinct of from ID and to ID, and loop through that group of things. And we're making a links list here, and so we're saying if the from ID is the same as the to ID, we're not interested. If the from ID is not already in my from IDs that I've got, I'm going to skip it. If the to ID is not in the from ID, meaning that this is a to ID that's not also, we don't want links that point off to nowhere or point to pages that we haven't retrieved yet, and that's what this is saying. So this is really going to give us, it's a filter on the from IDs and the to IDs from the links table, so that it only are the links that point to another page we've already retrieved. And then we're going to keep track of the entire superset of the to IDs, the destination IDs. And I'm just putting these all in lists so that I don't have to hit the database so hard. Okay, so this is getting what's called the strongly connected component, meaning that any of these IDs, there is a path from every ID to every other ID eventually. So that's called the strongly connected component in graph theory. Then what we're going to do is we're going to select new rank from pages where for all the from IDs, right? And so we're going to have a dictionary that's based on the ID, the primary key, that's what node is, equals the rank. And so if we look at our database,
Smash that like button,
means that
drop a comment
for
down below,
part
and
of the
subscribe to
strongly
Pro
connected
Free
component
Courses
in links,
Comp now.
We're going to grab this number and stick it into a dictionary based on the primary key of this, this number right here. So we're going to have a dictionary that's this mapped to that. Again, we want to do this as fast as possible. Now we're only doing one iteration at the beginning, so it asks how many times you want to run it. Okay, so we just make an integer of that. We check to see if there's any values in there. If there are no values, we are bad. And now we're going to go I equals 1 to range many. This is going to be 1 to 1, so it might run however many times. And then what it's going to do is it's going to compute the new page ranks, and so what it's really going to do is it's going to take the page rank, the previous ranks, and loop through them, and this is the previous ranks is the mapping of primary key to old page rank. Okay, and for each node, we're going to have total equals total plus old rank, and then we're going to set the next ranks to be 0. Okay. And then what we're going to do is figure out the number of outbound links for each page rank item. So node and old rank in the list of the previous ranks. These are the IDs we're going to give it to. And so for this particular node, we're going to have the outbound links, and we're going to go through the links and not link to itself, although we made sure that doesn't happen. We make sure that this. But then we're going to make a list called give IDs, which are the IDs that node is going to share its goodness. And now what we're going to do is we're going to say how much goodness are we going to flow outbound based on our previous rank of this particular node and the number of outbound links we have. So that's how many that's how much we're going to give in our outbound links. And then what we're doing is all the IDs we're giving it to, we started with the next ranks being 0 for these folks. These are the receiving end, and we're going to add the amount of page rank to each one. So whatever this is, so we'll go through all of the links, give out fractional bits of our current goodness, and it's accumulated in each one. And so eventually, all the incoming links will have granted each new link value. Okay. Now I'm just going to run through and calculate the new total, and this evaporation. The idea is that you can't. It has to do with the PageRank algorithm that there are dysfunctional shapes in which PageRank can be trapped, and this evaporation is taking a fraction away from everyone and giving it back to everybody else. And so we add this evaporative factor. And then we're going to do some computations just to show some stuff, and that is we're calculating the difference, the average difference between the page ranks. And you'll see this when I start running it. And that is telling us, this is going to tell us the stability of the page rank. So from one iteration to the next, the more it changes, the least stable it is. And you'll see in a sec that these things stabilize. And then we'd say, what's the average difference in the page ranks per node, which is what this is. And that's what we're going to print. And now we're going to take the new ranks and make them the old ranks, and then run the loop again. So I'm not actually updating the database each time through the PageRank iteration, but then at the very end, I am going to do the update for all of these things and update all of the rankings with a new rank. So I'm doing an in-memory calculation so that this loop here runs screamingly fast. Even if I want to do like this loop 100 times or 1,000 times, it's really all just in-memory data structures. Okay, so it's probably easier just for me to show you this. It'll be very, the code runs quite simply. Python 3 sprank rank.py. And so I'm only going to run it for one iteration, and that means that it's going to, this loop here is just going to run one time. And so it's going to start with the page ranks of the new rank of 1, and it's going to just run one iteration and put the rank there, okay? And then update this as well. So let's go ahead and run that once for one iteration. Okay, and so it ran one iteration, and the average change between the previous rank and the new rank is 1. So there, it's actually quite crazy. So I'm going to refresh here, and you'll see that the old rank was 1, and the new rank went way down, way down, way down, way down, down a little bit, down, down some, up a whole bunch, down, down, up. So you see that they went down and up. Now the sum of all of these numbers is going to be the same, right? Because all it did, it was like floated out and recalculated it. And so that's what happens with PageRank. And so what will happen is if I run one more PageRank iteration, these numbers will be used to compute the new rank, and then these will be calculated to the old rank. And so you'll see that these will they will change again. So I'll just run it one more time. So I'm going to run one iteration, and then I'm going to hit refresh. So you see all these numbers got copied over, but now there's a new rank that's computed based on these guys. And so they're getting, this one went up. This was 0.13. That's gone up a little bit. This one's gone up some more. This one's gone up. This one went down, right? So this one went down from 6 to 8. And you can see that the difference is now the average difference between this number and this number across all of them went from 1 point something to 0.41. And you'll see that with these very few pages, this PageRank converges really quickly, okay? So let's run it again. And I'll just run 10, and you will watch how this converges. Okay, so there you go, it converges. So, and you're seeing now after like 12 iterations that the difference between the old rank and the new rank, well, that's because it's that old rank. I'll run one more iteration so that you can see. So this old rank is less than, 0.005, so now you can see that these numbers are sort of stabilizing. This is the average, that 0.005 number is the average difference between these two things. Now, if we're going to pretend to be Google for a moment, we can say Python 3 spider.py. So let's just do 10 more pages. Now what's going to happen here is these new pages are going to have page ranks of 1. Okay? So let's get out. So if I do a refresh now and I look at new rank, so there's these guys that have high rank. What you'll see, I hope, yeah, okay. So you see new pages, right? These are the new ones that we just retrieved. I don't know if they're linked or not, and they all got 1. So some old pages are way up, 14. Some pages, if we go downwards, are way down, right? So these are like useless pages. They point to somewhere, but nobody points to them. That's what happens with these page ranks, okay? So what happens is the new records get this 0.1, and so if I run the ranking code again, and I run, let's just run 5 iterations, you'll see that the average delta goes up just briefly as it sort of assimilates these new pages, and then it goes right back down again. And so that's what's happening with Google. It's sort of running the spider to get more pages, then running the page rank, which gets disturbed a little bit, but then it reconverges very rapidly. And of course, they've got billions of pages, and we've got hundreds of pages, but you get the idea. Okay, and so I can run page rank like 100 times, and after a while, it just sort of hardly is changing. So that's 2.7 to the negative 10th power. So now, let me run it one more time to update the stuff. And if I refresh this, you're going to see, look at how stable these numbers are. 14, 9, 4, 3, 5, 9, 1, 5, 6, 7. The difference is there in the 7th one. So that's why this whole PageRank is really cool. It seems like it's really chaotic when it first starts out, and away you go. Okay? So that was just this, SP rank, right? SP rank, and SP reset, we can look at that code. I won't bother running it. It just sets the old rank to 1. That's it. That's as much code as you've got. It just restarts it and lets it rerun. So I'm going to stop now, and I'm going to start a new video where I talk about this phase here where we're actually going to visualize the PageRanked data. And what we are in the middle of is we're in the middle of the PageRank code, and we just got done running the PageRank, and so we have spidered the code, we've run PageRank a bunch of times. SP reset allows us to restart the PageRank algorithm if we want, but we're not going to play with that. We're just going to play with SP dump and SP JSON and do the visualization, which is the fun part. So I'll go into SP dump. So this is simple code because it's really just running a SQL query and then printing stuff out, right? So we connect to our database, create a cursor, and then just do a select count, and we're going to just show the number of links. We're going to order by the number of inbound links descending, so we see the most linked things, and we'll see the top 50 of that. So this is just a sample. You'll tend to write little helpers like this that make your life easier just to show you the kinds of things that you want. spdump.py, and like you just kind of test to make sure that's like, oh, this looks right to me, you know. And so here is the number of inbound links, so that's my blog that has the most inbound links, followed by my uncategorized, whatever that is, and these are the number of inbound links within my own blog somehow. I don't know, because this is not looking at the whole internet at all. So there we go. So that's SP dump, pretty straightforward. And now we're going to go through the visualization process. And so this is going to look at all that data and produce some file, a JavaScript file. It's going to write a JavaScript file that will then be fed into my visualization using D3. And SP.json is going to do a big long join. It joins the links with the thing, and where HTML is not null and error is not null. You know, order by the number of inbound links. So we're looking at the things that have the highest number of inbound links. We're going to read all this stuff. We're going to read through all those rows and pull out the page rank for each one. We are looking for the highest and lowest rank because these numbers can vary quite widely. They go all the way from 0.000 to 20 or 30. And so it asks how many do you want to do, so it only does the top like 20 or something, and you'll see why we need that in the visualization. And so this is just checking. And so we're going to write out a file. We'll see what the format of this is. It's just a JavaScript file, and we're going to write out. We're basically normalizing the rank. We're subtracting the minimum rank, and because we're going to turn this into line weight, the thickness of the line, and so we're dividing by, we're normalizing the rank to be the thickness of the line and the size of the ball. You'll see all this, and so this is really just writing some JavaScript with the little strings and stuff like that, and then we're going to finish the JavaScript, and then we're going to write all the links out. So these are the balls that you'll see. And this is showing this is drawing all the lines, and this is again normalizing things for thickness and printing these things out. Now I don't want to go through this in tremendous detail, but so I'll do Python spjson.py. Let's do the top 20 nodes, and if I take a look at this file spider.js, you can see that it's some objects that basically put the page rank in, which ID it is, and that's a way for me to be able to link back and forth. Weight is how big the little circle is, and then I have the links. And I only asked for the top 20, right? And then this is the thickness of the line, where the line starts, where the line ends, okay? So this is read by this HTML file, and it's going to read somewhere this force.js file, and my own spider.js code. This is some JavaScript. I mean, no, the force.js is the visualization code, and this is D3, the visualization library. So I'm using this d3.js, which is a really great visualization library, and this is just drawing the circles and making the circles colors and making the circles bigger and smaller, and then connecting all the lines in between it. So this is just there. This data feeds that thing. And so when we're all done, you simply say open. You don't have to do anything. Open force.html. And so all this beautiful JavaScript stuff is like, oh wow, that's really cool, because you can move these things around. Whoa! You can see the circles are bigger. If you hover over it for a while, it shows you the big ones. You know, you can see these things, and it's kind of cool. So I gave you all this force.js and force.html, and so that kind of visualizes the page rank. And you could, you know, use this to visualize quite a bit of stuff. You know, it'll take you a while to pull down enough data from a real website, but after you pull down 400 or 500 pages, if you have some time, and then the visualization is quite interesting. But you can see why we had to pull down several hundred pages just to get this much page rank information. Okay, so that gives you a sense of how to run the page rank code in Python for everybody. So thanks for listening. The last visualization application that we're going to take a look at is mailing lists, and that's kind of ironic. We started with the mailing lists, and we're going to end with the mailing lists. The mailing lists, of course, are from my open source SUSCRIBE project, which I love and very proud of. And so what we're going to do is we're going to crawl the archive of a mailing list, and then we're going to do two visualizations. One is a activity visualization, and another is a word cloud. So it's probably the more important thing is when I do the demonstration of how the software works. So this is a large data set, so you got to be careful. This could spider gmain.org, which is a very free and friendly archive. This data originally came from gmain.org, but I've got a copy of it. And so gmain.org is not rate limited, but if everyone who is watching this starts spidering gmain.org at the same time, you will crash it. It just doesn't have the horsepower to give you this data as fast. And so I've got something that can give you the data super fast and has no rate limit on a really good server, and it's cached all around the world using a technology called Cloudflare. So please, please, please don't point this at gmain.org. Point this at the URL here, mboxdrchuck.net, etc., and then you can run this as fast as you like. Now, another thing to worry about is if you have a metered connection. So don't do this on a cell phone connection, because you'll pay thousands of dollars perhaps. Make sure you run a no-cost connection before you start running this, because this is going to pull a lot of data down. If you just start this from scratch and you let it run, it on a super fast connection, downloading the whole thing is probably about 4 hours. On my home connection, when I had like about a 10 megabit connection, it took several days. And so just understand that in this one, it's both fun to deal with a ton of data, and it's scary to deal with a ton of data. So this one is big. This one is, you'll see the process in action because it'll run for a while. The things will take a long time. So here's basically the flow of the data in this particular one. You are going to have the restartable spider that talks to the API, mboxdrchuck.net, which has a scalable copy of all this information. And again, it's going to do kind of a raw database, not a very clean database. It's sort of a mess. It's just enough columns to keep track of whether or not we've got this page or not. And so this has, you know, the ones we've retrieved so far. And so what Gmain does is it sort of scans down to see where to retrieve next, gets that, and then starts scanning and then adding things here. So it just adds it, and then it blows up, And then it comes in again and says, okay, I'll start here, and then it starts retrieving stuff and fills this in, fills this in, fills this in. And sometimes you put like a delay in this so you don't overwhelm networks or don't overwhelm servers. But basically this is pretty much a raw retrieval of the email messages. And this file can get rather large. This is the one that's greater than a gigabyte. Now this data is actually really nasty. It's email data. The date format's changed. This is data that lasted from 2004 to like 2012 or 13. And so this data is got a lot of things wrong with it. It even has things where people's email addresses changed. And so it has this mapping file. This comes along with it. This mapping file that says, here's this one person, and here are the 6 email addresses that they used throughout the life of the project. And so there is a relatively complex, and so this part here is super slow, very slow. This part here is slow, but it'll take, like, depending on how fast your computer is, somewhere between 2 minutes and 10 minutes. This first part will take days, perhaps, depending on the speed of your network connection. And so what Gmodel does is it reads through this, it actually recreates, it wipes this out and recreates index.sqlite every time it runs, so that you can change any number of things, you can respider things, you can do whatever. And often the cleanup, this is one of those cleanup processes, and you have to tweak the cleanup process. You like look at your data like, oh, the cleanup missed something, so I got to run it again. So this produces index.sqlite every time it runs. So this is like 2 to 10 minutes. Gmodel is 2 to 10 minutes. And it like maps names, and when it's all said and done, this is a very small, highly normalized, it's a nice data model. This one here had the Content SQLite has an ugly data model. Index.SQLite has a pretty data model. It's got foreign keys, it's got all this stuff, and all those things we talked about in the database where it's efficient. And so in your mind, keep track of how fast it is to scan all the data in a database with a bad model, and then watch when you run like gbasic, which is a scanner, or gline, which produces line data, or gword, and watch how fast they run. They run in like a couple of seconds at the most, and this runs in 2 to 10 minutes. And the difference is that's because the data is efficiently modeled in index.sqlite. So you can take a look at that using SQLite browser and take a look at the data model, and you'll see it looks just like the stuff we talked about in the database chapter. It's got foreign keys and all those things. And so that runs, and you got this, and then we do our visualizations and our analysis from this clean version of all the data. And so gbasic just loops through and prints some stuff out. It's a great way to test things. It's a pretty easy to understand program, and you could take a look at it. Gline does some bucketing and makes some histograms to produce a line graph. And then gword does a different histogram. It does a histogram of word frequency and then produces that as the word frequency ends up in gword.js. And then we have 2 HTML files that use the d3.js visualization to produce a line and a word chart. And so, you know, in another video I will show you how this code works, which is probably more useful than this picture. But this is a whole bunch of good stuff in this particular application, and if you really understand everything in here, you can build a pretty sophisticated data retrieval and analysis pipeline. And so that's it. I thank you for watching all these lectures, and look forward to seeing you on the net. We're doing some code walkthroughs. If you want to get the source code, you can take a look at the sample code and download it and work through it. And so what we're working on now is doing some retrieval and visualization of email data. It's kind of ironic. We're going to now look at the email data that we that we started with. It's the same Sakai developer list email data. And so there's this service called Gmain. And Gmain archives developer lists and various email lists, and I've made a copy of their data because all the students in my class hitting their server with their API would crush it. So in order to be a nice guy, I put up a much more powerful server with just the data from this one list. And it's about a gigabyte of data, so be real careful if you're paying for network. So the basic process we're going to go through is we're going to have a spidering process that's a simple, restartable, focused on the network problems, data pulling to pull content.sqlite, and there's going to be a database there. And then we're going to have a cleanup process. This database is going to get large, about 1 gigabyte. And then we're going to have a process that kind of grinds through this data. It takes a while. And so then it's going to read this mapping, and I'll show you that when it comes, because things like people's names have changed over all these years. And it does a cleanup and makes a really nice, highly relational version of this data. And then we visualize from here. And so this could take you several days to finish this. This will take like a few minutes to run, and then this will just take seconds to run. And so this is a multi-step process where if you were doing something like running something for 2 days to produce a visualization, and it blew up 3/4 of the way through, it would do you no good. And so that's why we break this into simple parts. But right now we're just going to focus on this part right here, and take a look at the mail bit. The mail bit, and retrieve the mail, and then we'll have another video to talk about the rest of this stuff. Okay, so let's take a look at the code. So here is gmain.py. That is the basic code, and it's hopefully this stuff is starting to look familiar. The thing that's weird here is we got to do some date time parsing. And there is code that's out there, but you may have to install it. And I had to write my code in a way that didn't assume that you could install the date-time parser. And so it has it, even if that's not there, it uses my own date-time parser, and that's what this code is. Don't worry too much about that. And of course, we have to deal with the lack of certificates inside of Python. And so we start things out. And this is really a simple table. We've got a messages table that's got a primary key, the email itself, when it was sent, what the subject, and the headers and the body. Okay? And so what we're going to do is, because we have to pick up where we left off, we're going to select the largest primary key from the messages table and retrieve that. And then we're going to go to the one after that, okay? And so we know what the ID is, and we're going to pick up where we left off. And so we have a starting point, and it starts either 0 or 1, and we're going to ask how many messages to retrieve. We've got some counters, and so we're going to say, okay, see if select ID for messages where ID equals whatever that starting is. That's the highest number we've seen so far. And if row is not none, that means we've already retrieved this particular email message. Otherwise, we're going to keep on going, and we're in good shape. And this is one that we want to retrieve, and we're subtracting that so we don't. And so this is the base URL. This is the URL of our API, the one that I copy. I have a nice copy of all this data on a server that's accessible worldwide and won't crash. So the format of this is, you can say I would like the email address for from 1 to 2, or from 100. Oops. From 102, 101, message 101 to 102, and we can just kind of walk through these things. So that's the message ID. And so if we're going to make the URL, we're going to take the base URL, add the starting address, and then add +1. So we got the slash at the end of the starting address, and so that's how we form those. And we're going to retrieve that, and we're going to decode it. We've seen this in some other ones. We're going to check to see if we got legit data. If not, if I got a 404 not found or something else, we're going to quit. If someone hits Control-C, or Control-Z, we'll get the program interrupt, and we'll stop. If there's some other problem, right, we're going to complain and keep going. And if we have 5 failures in a row, we're going to quit, but it will just keep on going, because these things do have glitchy bits here. And so at this point, if we've made it this far, we've retrieved the URL, and we've got the number of characters we've retrieved. And if we get bad data, if it doesn't start with from, because this is a mail message, right? And they all start with from space. If it's right, it starts with from space. Then what we're going to tolerate up to 5 failures there for bad data, because it could be bad. And then we're going to find a blank line, because that's the new line at the end of one line, and then a blank line. And then we're going to take and break this into the headers, the mail headers, which is, that mail headers is this stuff right here, up to, but not including the blank line, and then the body is everything after that, okay? And so we'll just break that into pieces, otherwise we'll complain and tolerate up to 5 characters, and then we're going to use a regular expression, kind of from the regular expressions chapter, to pull out an email address from the colon line somewhere in these headers.
Smash that like button, drop a comment down below, and subscribe to Pro Free Courses Comp now.
Come on. Pull this stuff out up to it. So you got the less than, you got the parenthesis, you got 1 or more non-blank characters followed by an @ followed by 1 or more non-blank characters, and we'll get back a list of those. We should only get 1. If we find 1, we're going to grab the email, we're going to strip the lowercase, and if we got some little nasty less than sign in there, we'll tolerate that as well. So this is kind of cleanup, and you get used to this where you're like, oh, how come all those email addresses have this other stuff in them? And then we also look for it if there are no less than signs, and we do this way. And that's different. Some mail messages have it this way, and others, again, you write this code after you watch it for a while. You're like, oh, it's crapped out and giving me bad stuff. And I make them all lowercase so they match better and get rid of bad characters. Well, now I got an email address. Then what I do is I look for the date of this. So I'm going to graph these by date. So I look for this line and use a regular expression to pull that out, right? So I'm looking for a date followed by a blank, followed by any number of characters, followed by a comma. So I'm not interested in this Wednesday bit, so I'm skipping that bit right there and going and grabbing everything after that comma space. And so it's really here to the end of the line. So that's the new line. And so it's going all the way. It's going to pull this bit right here. That's the text. And this is where we're going to like say, oh, that's kind of a funky looking date, and we want to standardize that date. So we're going to, let's see. Yeah, we're gonna chop it off at the 26th character. Apparently, I don't know what the 26th, why we care about the 26th character, but we chop that off at the 26th character. And then we're gonna parse it, and that's gonna give us back a nice clean date, sent at date. Otherwise, we're gonna complete, we're gonna quit. And if we can't parse it, then we're gonna tolerate 5 bad email addresses in a row. Then we're looking for the subject line using another regular expression. Subject line. Regular expression, that's pretty easy, up to but not including, right? There's a blank there, it's the subject. And we pull that out, we get the subject. Now at this point we parsed it and we got good stuff, so we reset the fail counter because I kept saying if you fail 5 straight times you quit. And we're going to print it out, and then we're just going to insert that stuff. We've got the ID of the message, which we've got the email address that it came from, the time it was sent, the subject, and then basically the headers and the body, and we're just inserting it. And now we're going to say every 50th we're going to commit it, so that speeds things up, and every 100th we're going to wait a second. So that's, count is going up, 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 and every 50th you'll see it pause, and then it will, every 100th it'll pause for a second. Mostly that's to let me hit Control-C or to not overload any server. Okay, so that's the simple one. The problem is this data just gets ugly, and so you'll find yourself wanting to reset this and start it over. This one's going to work, of course, but it's...
Are you ready to unlock the power of programming? Welcome to Pro Free Courses Comp, the one-stop destination for all things coding. With us, you're not just learning, you're embarking on an exciting journey into the world of programming. Imagine having access to over 100 comprehensive courses from the world's top universities all at your fingertips. From Microsoft Office to Google Workspace, from Python to JavaScript, from React to Node.js, from beginner to advanced, it's all here and it's all free. This isn't just about learning to code, it's about mastering the language of the future. joining Pro Free Courses. Comp means becoming part of a community of learners, developers, and innovators. It means stepping into a world where learning never stops, where every line of code you write opens up a new universe of possibilities. So why wait? Subscribe now and take the first step towards coding your future. With Pro Free Courses Comp, you're not just learning to code, you're learning to create, innovate, and transform the world. Pro Free Courses Comp. Learn, code, your path to success.
These are hard to build, and that's why it's a good idea. Python 3 gmain.py. How many messages? Well, let's just do one. Okay, so it went and grabbed, oh, do I have this already running? 51 through 52. Let me start over. +-l star SQLite. Okay, RM content. I must have run it to test it. So let's run it again, Python gmain.py, and ask for one message. Okay, so there we went and got message 1 from 1 to 2. We got 226 characters, and we printed out the email address, the time we got it after all that hacking, and the subject line, and that's what we got. So if we take a look at the database, and we go into the gmain, every time you see the content SQLite journal, that means it needed to run a commit, and it hasn't run a commit, but I'll hit enter and that will do the commit, and you see that vanish. So now I can open it and I take a look at, how come there's no messages? Did that one not get stored in there for some reason? Just refresh. Huh, well, let's run it again. Maybe it didn't commit. Maybe I got a bug in it. Let's make a change to the code. I'm going to see this connection.commit. See that? Connection.commit. Going to commit there. And the other thing I'm going to do is every time I stop to read, I'm going to commit right before I read it. So I think we should, I hope that doesn't blow up. We'll see. So the idea is that if I want to stop, I want it committed. So let's do this. Let's do one message. And now I should hit, is it committed? Now that I've put the commits in, I think that it will look better. I can't refresh, and so there it is because I committed it, and I don't have the journal file, so that's good. So that's a good idea to put those commits there. So I'll just leave those commits in. When you download it, it'll have those commits in there. So again, I put a commit here and a commit at the very end to make sure, and then I missed that. But now we get one, right? And so let's just run it again, and you'll see how by selecting the max of the ID, it's going to select the max of this and then add 1 to it, so it doesn't do the next one. So if I run it again, I say give me one message, so it goes 2 to 3, and give me 2 messages, right? So I hit enter, and I can do refresh, and now you see we've got 4 messages. Okay, and so let's just fire this baby up, tell it to get 100. Run, right? It just goes and goes, and it pauses once in a while to do a commit. And if I made a commit every time, it just paused there. Now it finished. So this will run, and we will get a bunch of data. The problem is if I just run this, it'll take about 5 hours, okay, to run this and get this all. And I've got a really fast connection, so I have got a file that you can download. Let's go find it. Let's see if I can, let's see how long it'll take me to download this. I've got a file that you can download and save. Now I'm going to use the command line curl, or wget is another command that we Linux and Mac people can use. I don't know, you might have to use your browser to do it. Let's see how long this is going to take. It's retrieving. Minute 30. Okay, well, I'll just wait when this come back. Okay, so now that's done. I was averaging 10 megabits a second. I downloaded about 600 megabytes, 10 megabits a second. That will probably be slower for you. But so now if I take a look, you're going to find that that content.sqlite is 624 megabytes. Now what happens is I've pre-spidered this, and so now if you run gmain.py and ask for 5 more messages, it will pick up where I left that one off. So it's up to message 59,000. And I think that, oh, you saw an error. See, you saw a bug in that one. I don't know what's wrong with that one. So let's see if, so at this point we're going to have most of the data. It might find its way to the very end. Once you get this, it should be not too much more. I don't know, maybe it's like 63,000 or something. So what we'll do is we will let that run, and we will come back when that one's finished, and run the next phase after it's got all of its data. Okay? So thanks for listening. The work that we're doing right now is we are in the process of building a spider and visualization tool for email data that came originally from this website Gmain, but I've got my own copy of it. And so what we've done before is we ran gmain.py, and I grabbed a URL. I have a URL that has all this data, and I downloaded that, and then I ran Gmain again to catch up. So it took quite a bit of catching up. But by the time I get to, remember how I said it tries to fail 5 times? Well, it ran out of data at 60,421, and then it started failing, and then it quit. And so we pretty much have all of our data now. We have finished this process in content SQLite. Okay, and if I take a look in the database browser, we can see we got 59,823 email messages. And so if I look at any of these things, you see the headers, you see the subject line, you see the email address, you see the body of it. So remember, I split the body in half, and headers, and so I made this as raw as I possibly could, because as you saw, I had to spend so much time in the Gmain just getting the data successfully retrieved, and so I don't like cleaning the data up too much. And so what we're going to look at next is the data cleaning process. Okay, and so this is gmodel.py is the code we're going to take a look at now. So let's get rid of those guys and look at gmodel.py. I don't think I need URL lib in this code. Do I have any URL lib? No. So I don't need that. Sorry. Fix that. Okay. So it's going to read from the database. It's got to call. It's going to use regular expressions, and zlib is a way to do some compression. And so I'm going to do in this one. I'm going to compress some of the data to make it so that I have less data. Some of the text fields are going to be compressed. I wanted to keep these fields uncompressed inside of messages, so we have some just cleanup messages and cleans things up. And it turns out that the way email addresses in this particular mail corpus, they changed over time, and there's certain kinds of things. Sometimes the gmain.org is the email address when people want to hide their address. And I made all kinds of stuff, and I split it and checked to see if it ended with this, and I cleaned up things, this, that, and the other thing. And so I have all kinds of cleanup stuff going on in here. And I have this mapping and DNS mapping that I'll talk about in a bit, where organizations sometimes sent email with different addresses over time, and people sent email from different time. And we're going to do the parsing of the date, and that is the code for that. We're going to pull out the header information. This is sort of borrowed from the other code. We'll clean up the email addresses and the domain names. And we'll pull the date out, pull the subject out, pull out the message ID, various things. So here's the main body of the code. We're going to go from content.sqlite to index.sqlite. And what I'm going to do every time is I'm going to wipe out index.sqlite and drop the messages, senders, subjects, and replies. So this is a normalized database in that it has foreign keys. So there's a messages table here with an integer primary key, the GUID for it. The GUID stands for Global Unique ID, sent time, sender ID, and it's going to have a blob. These are blobs, binary large objects for the headers and the body, because I'm going to compress them in this database to make them. And then the senders each sender has a key, and then subjects, each subject line is going to have a key, and then replies are a connection from one message to another, and so this is like a many-to-many. Now, I also have this file called mapping.sqlite, and so we can take a look at that one, mapping.sqlite. And so what happened is this has two tables that I hand deal with, and so sometimes Indiana, this was a email address that mapped to that. So indiana.edu, that's a way to take an @'s the email address, and then these were a bunch of people that had email addresses changing throughout the project, and I sort of kind of mapped them in a way. And so this is just sort of like I pull this in really quick, and I read all this stuff from the DNS mapping, and other than stripping and making this lowercase, etc., I just am going to make a dictionary. DNS mapping, which is the old name to the new name, and the email address mapping from the old name to the new name, and I'm using fixed sender. Fixed sender is because the email addresses, even within Gmain, were kind of funky. So don't worry so much about this. Okay, and so now what I'm going to do is I opened up a connection just to read all that stuff in, and now I'm going to actually open the main content. And I'm asking it to open this a little trickier. I opened that read only. That was so that I could potentially be running the spider and running this at the same time. I get a cursor. And so I'm going to read through, so in the content file, this is the big one, I'm going to read through and go through every one and write all of these things in. And I'm going to take all the email addresses and I'm going to put those in a list. So I loaded that. I've got the mappings loaded. And so now I'm going to go through every single message. I got all the senders, all the subjects, and all the global unique IDs. So I read in each message. So now I'm going through content one at a time. I parse the headers. I check to see if the sender's name, email address, after it's been cleaned up, is in my mapping.get sender, and the default is I get back sender. That's what that's saying. Look up sender. If it's in there, give me the entry of that key. Otherwise, give me sender back. We're going to print every 250 things we do. We'll complain if this is true. We're going to go get the mapping between the senders, which is a way to look up the primary key. I could have done this with a database thing, but I wanted it to be fast. So that's part of the reason I read all these things in, so I could have those mappings to be really fast. You'll see this takes a little while, even though it, even though it's I got all this stuff cached. And so then, if I don't have a sender ID, meaning that I haven't seen it yet, then I'm going to do an insert or ignore into senders, and then I'm going to do a select, and then you've seen this where I grab the row back and I'm really just trying to look at the recently assigned ID, and then I'm going to not only set the sender ID for this iteration of the loop, but I'm also going to store it in the dictionary, and so that builds this dictionary up. And you'll see the same thing is true for subject ID. I'm going to insert it into the subjects table and get a primary key if I don't know what it is. And then I'm going to put it into, not only am I going to put it into the database, but I'm also going to put it into my dictionary. And the same thing, I guess I didn't do it for the GUID. Okay. So now what I have is the sender ID and the subject ID, which are foreign keys, into the sender table and the subject table. And I'm going to insert the message with the sender ID, subject ID, the sent at, headers, and body. And the values here are the GUID, sender ID, subject ID, sent at. Now this here is zlib compress. So what I'm taking is the message, the header, and the body, and this little bit ends up with a compressed version of this stuff, and you'll see it in a second. And this keeps the size of these text things down at the cost of the computation of, at the cost of the computation to compress and decompress when we want to read it, okay? And then I pull the GUIDs out, the ID, which is the GUID, and I pull out the primary key for this thing based on the GUID, and I update this dictionary, okay? So let me run that code. It is doing a lot of cleanup, and I'll tell you, it took me a long time to make this work. So this code that I'm running now, oh, don't forget to take a Python 3, Chuck. So this is going to run every 250. So it did all this pre-caching, so that's how long it takes to do 250. Now there's 60,000 in here. And so this is really busy. The reason it's bouncing back and forth is that every time it makes this journal file, and then does a commit. So you can kind of see that it's busy making journal files and committing, and there's a lot of activity going on here. Just so happens that Adam shows me these files. Okay, so it finished. It took about 3 minutes to finish that, right? And so if we take a look at the size of the files, we will see that the index is much smaller. It's fully normalized. It's still 263 megabytes. It's all compressed. So let's take a look at that in the browser. So it's 200 megabytes, but it loads up a lot faster. There we go. So we have a senders table, right, which is just kind of a many-to-one table. We have a subjects to table, which is a many-to-one table. And we have messages, which has foreign keys. It takes a little bit to load that up. Okay, and so we see the foreign keys for sender and subject, and that saves us. All those foreign keys save us. And so we have, you can kind of see that I can't see the headers in the body because now they're compressed. That saves me a whole bunch of stuff, right? It saved me a whole bunch of stuff. You know, and so that's what's in that file. And that we've finished this process, okay? And we've finished modeling the data and making it really clean, and we'll pick back up, and the rest of the stuff we will do is actually visualizing pulling data out of index.sqlite. The idea is this can be restarted, this can be run over and over and over, even though it takes like 3 minutes to run this. That's way better than 5 hours to run this. So 3 minutes, 5 hours, and then we'll see now reading this is in seconds because we got it all nice and normalized in a quite pretty way. So I hope this has been useful. In the next one, we'll actually do the visualization. We are in the process of retrieving data from this Gmain server, one that I've made a copy of. And we have so far spidered it all. Ended up with 600 megabytes of spidered information. We have ran a rather complex cleanup process that you probably don't need to fully understand. You can look at it for patterns, but in general, the cleanup process will be very sensitive to the data. And then we have this index.sqlite, which is 260 megabytes right now. And we're going to now do the fun, easy bits here, where we're going to run little queries that just pull data out. And so these are much simpler. So part of what I wrote when I was doing this is I wanted to do some simple basic calculations on the data to make sure. I really was sort of looking for anomalies, right? What was working, what wasn't working. So I wrote a series of really simple things like this gbasic. The gbasic code just give me some basic data, right? So I wrote things down and I counted things, and so do I need URL lib request in this one? I don't think so. Let's fix that bug. It's not there. No reason to put any of that stuff in there. So it reads that index.sqlite, which is our cleaned up data. It reads through and makes a dictionary. This pattern you're going to see a lot, where I'm going to make a dictionary of ID to senders, save myself repeatedly looking at things. I'm going to grab the subjects. I've cached them all. I could have done this all with SQL, but I just wanted to do things faster. And now I'm going to go through each of these messages and make a dictionary of them. I'm going to put a lot of stuff in memory, and then I'm going to do some counts. I'm going to see who is sent the most, right? The organizations. And so now I've got to go through the all the messages. I am not actually, so you'll notice that I'm not selecting the body or the headers here. I am just getting sender ID, subject ID. I probably could have done this with a join. It would have been cleaner. You can do that. You can make that change. Do that with a join so it's cleaner. So I'm going through all the messages except not the body, so this is going to be really quick. And I'm pulling out the sender's ID. I'm breaking the sender into pieces. See, my data's clean now. I cleaned it all up in the previous processes. And if I don't have two pieces, I continue and I get the domain name. So I have the person. I'm doing a basic dictionary histogram for the people and the domains. And then I'm going to sort them, right? With a sorted, and we're going to grab the key. We're going to sort it by the how many there are, reverse, and then print out the top few of the organizations and the top few of the people. Okay, so we'll just run that code. Python gbasic.py. Let's dump out the top 10. So we loaded 59,000 messages, 29,000 subjects, and 1,800 senders, and figured out the top 10 people and the top 10 organizations. And you can write various things like that just sort of scream through your data, and it's good to get sanity checking on your data. Okay, so that's gbasic. Now I want to do gword.py, because that's kind of fun. gword.py. I don't need URL lib. Why do I keep putting URL lib in all these things? So we'll get rid of that. So this is really simple because I'm just going to go for the words in the subject line. And so I go through index.sqlite. I read in all of the subjects. And I make a dictionary of those. And then I go and find all the subjects. And then I'm doing this code right here. I'm pulling out the subject based on the message, and I'm doing this so that when the subjects are used more than once, I count the words more than once. This stir make trans, I talked about that in an earlier chapter. This basically throws away a punctuation in numbers, so that when I make my words, I don't end up with words that are like dashes. It compresses them down. Then I strip it, I convert everything to lowercase. This is basically just to keep too many words from showing up. Then I do a split, and then I got a counts, a dictionary. So this is a no punctuation, no numbers dictionary count. And then I just take and do a dictionary, and then I sort them in reverse order. And then I figure out what the highest and lowest is by running through I could have probably done this with a max and a min if I felt like it. And so now I have the highest and the lowest. Yeah, I should have done a max and a min on that one. Why did I do that? But oh well. And now I've got to spread out the size, and so I'm going to produce this file gword.js, which is needed by the visualization because it's going to use d3.js, a word visualizer, and gword.js, I have to tell it how big the text is, and so I'm doing some text normalization. Took me a little experimentation. So if I run this now, and I say Python gword.js, and I say Python 3 gword.js, which is a lot better. Oh, not Python. Okay, so now I can go look at the gword.js, wherever that is, gword.js, yep. And so this is basically, it normalized all the frequencies and made it font size. These are font sizes now, okay? And so this is just the data that's needed by this gword.jm, which uses this D3 visualization.
Smash that
word
like
cloud
button,
code.
drop a comment
So
down
this
below,
pulls in all
and
my
subscribe
data,
to
and
Pro
then
Free
this is
Courses
just
Comp
some
now.
JavaScript that draws the picture in on the page, okay? And so the easy part now is to just open gword.htm in a browser. It just so happens on a Mac I can do this. And so that gives me a word cloud based on that data. It kind of randomizes it and shows different stuff, but it's using this, oops, it's using this data to generate how big those things are, and then using a bit of randomness and simulated annealing to lay it out. That's not stuff that we actually have to worry about, okay? So that's how we get to the point where we're seeing a word cloud from this. Now we're going to do another visualization, and this time we're going to do a line visualization, and we're going to create a thing called gline.js and produce with another HTML file. We're going to use D3 and produce that output. So let's say goodbye here, goodbye, 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 goodbye. So gline.py, get rid of that file. So again, I'm going to preload all of the senders in this case. And again, I could have done this with a join, probably should have done this with a join. I'm going to preload all the messages, the sender ID, subject ID, etc. I'll load those up. And now I'm going to read through. I'm going to have the sending organizations and the senders. And I'm going to split the senders, and I'm going to have the sending organizations, and then I'm going to do a simple dictionary as I accumulate the sending organizations by splitting the person's name into @signs, and then based on the organization I accumulate it, and then I sort them, and I pull out the top 10 organizations, print those out, and now I'm going to break this down into months. And I'll show you what this looks like in a second. Let's go to the gline.js. So the month looks like this. Okay, so the month looks like that. So that's the first 7 characters of the date. So if we look at the date looks like that, and the month is the first 7 characters. And this is the data that I've got to give it. We'll clean that up in a second. That data will look better in a moment. Go back to gline.py, and so this is we're doing the key is a tuple, which is the month, and which organization that did it, and it's only in the top 10 organizations. And then we're going to do we're going to basically do a dictionary where the key is a tuple, and then we're going to sort it, sort by key in this case, not by value. That's in the months is going to sort that, and then we're going to write all this data out into gline.js. So let's go ahead and run this. And again, this is just the data that has to be written in a way that the JavaScript can understand it. Python gline, Python 3 gline.py. Okay, so top 10 organizations. So now let's take a look at that JavaScript. So this is what it looks like. So it just so happens that you got to tell it these are the data points, these are the lines. So this is the year, the line for University of Michigan, gmail.com, swinsburg.com. So this first column is that line points, and the next line points. So all this code was to get the data in such a way that I could produce this JavaScript file, because if I look at gline.htm, I need that data in that particular format, and I've got all this stuff. I make a line chart and I draw it with this data. That data, I had to go read all the documentation on how to figure this stuff out, right? And that's the data that I'm going to use, and I had to figure this out, and I had to transform it and make it pretty. It took me quite a while to get this to work, and this is not a JavaScript class nor a how to visualize in D3, but basically we pulled all that stuff in, and here's the G line that came from the JavaScript, and then it makes an array to data table, and then that data table is what G line draws. So with no further ado, let's open gline.htm to show that data. So there you go. That's the Sakai developer participation from 2015 through 2005 through 2015, based on which organizations did the most commits in Sakai. And so I know that I haven't done this all this code full justice. There's a lot of code here. The fun is just to kind of run it and see it, and then when the time comes to come back and see the techniques that are used when you're trying to build your own visualization pipeline. So I hope that you found this useful. This is a lot of code, hard to explain in 15-20 minutes, but I hope you take some time and look it over, and I hope you found all these videos. This is kind of the last walkthrough video for chapter 16 of the book, and so I hope that I will see you on the net.
Are you ready to unlock the power of programming? Welcome to Pro Free Courses Comp, the one-stop destination for all things coding. With us, you're not just learning, you're embarking on an exciting journey into the world of programming. Imagine having access to over 100 comprehensive courses from the world's top universities all at your fingertips. From Microsoft Office to Google Workspace, from Python to JavaScript, from React to Node.js, from beginner to advanced, it's all here and it's all free. This isn't just about learning to code, it's about mastering the language of the future. Joining Pro Free Courses. Comp means becoming part of a community of learners, developers, and innovators. It means stepping into a world where learning never stops, where every line of code you write opens up a new universe of possibilities. So why wait? Subscribe now and take the first step towards coding your future. With Pro Free Courses Comp, you're not just learning to code, you're learning to create, innovate, and transform the world. Pro Free Courses Comp, learn, code, your path to success.